Picture this for a second. You're standing on a completely calm, peaceful mountain. The birds are singing, the sky is clear, it's a beautiful day. Then, out of nowhere, the ground just begins to shake. You hear this deep, terrifying rumble echoing beneath your feet, and massive cracks literally tear across the earth. Within seconds, a tower of fire bursts upward. Rivers of molten rock are racing down the slopes, and a massive column of ash climbs a mind-boggling 30 kilometers into the atmosphere. The entire landscape is just changed forever.
It's an absolutely terrifying, yet totally awe-inspiring image, right? And it naturally makes us wonder, where does all this fire actually come from? Like, why does the Earth just suddenly explode like this? And why do these incredibly violent eruptions only happen in very specific places around the globe?
Okay, let's get into it. When you hear volcano, you probably just picture a mountain that erupts, but that's really just the surface result. A volcano is actually an opening in Earth's crust. It's essentially this massive escape valve for the planet. It's a place where molten rock, intensely pressurized gases, and ash can finally break free from deep underground.
To truly wrap our heads around this, we have to travel way, way down into the Earth's interior. We're talking about venturing all the way to the Earth's outer core. This is a layer of liquid iron and nickel that reaches a staggering, scorching 5,000 degrees Celsius.
It really helps to think of the Earth kind of like a giant egg. You've got this super thin outer shell, our crust, which is only about 5 to 70 kilometers thick. Right beneath that lies the mantle, this massive 2,900 kilometer deep ocean of incredibly hot rock. Then you hit the liquid outer core and finally the inner core, which is a solid sphere of iron under so much pressure it stays completely solid even though it's as hot as the surface of the sun. Because of all this intense heat, the mantle is slowly circulating in these enormous convection currents, with hot material constantly rising and cooler material sinking.
Now, these deep, churning currents are unbelievably powerful. They actually push the massive tectonic plates that make up Earth's crust, which are basically just floating right on top of this mantle. Now, they don't move fast, obviously. They drift at this incredibly slow speed of just a few centimeters a year, which is about as fast as your fingernails grow. But over millions of years, those tiny little movements are literally enough to reshape entire continents.
And here's where it connects to our volcanoes. When these giant tectonic plates pull apart or smash together at their boundaries, they trigger intense volcanic activity. In fact, a whopping 75% of the world's active volcanoes are clustered right around the Pacific Ocean in a zone perfectly named the Ring of Fire. So whether plates are pulling away from each other, like at the Mid-Atlantic Ridge, or diving underneath one another, these boundaries are the undisputed birthplace of Earth's greatest eruptions. Deep down at these boundaries, temperatures can easily top 4,000 degrees Celsius. Under the right conditions, that intense heat partially melts the solid rock into what we call magma. And just to clear up a super common point of confusion here, magma is simply the molten rock beneath the Earth's surface. The second it breaches the surface, boom, it's called lava. It's the exact same stuff, just a change in location.
Okay, so we know it's incredibly hot down there, and we know the rock melts into magma, but what exactly forces all that heavy, molten magma to defy gravity and travel all the way up toward the surface?
Well, rock essentially melts and rises thanks to 3 distinct physical triggers. Sometimes, as hot rock moves upward, a sudden drop in pressure allows it to melt even without any extra heat. That's decompression melting. Other times, sinking ocean plates release trapped water, which chemically lowers the melting point of the surrounding rocks. And occasionally, it's just pure heat transfer from deeper, rising magma. Once that magma is formed, it's less dense than the solid rock around it, so it naturally rises up, exactly like a hot air balloon floating into the sky.
But here's the thing. Before an eruption actually happens, this rising magma doesn't just blast straight out of the ground. Instead, it pulls into a massive underground storage tank known as a magma chamber. Over time, more and more magma pumps into this chamber. It fills up, building immense pressure as trapped gas bubbles expand, and that pressure begins to violently crack and fracture the surrounding crust.
Eventually, a pathway opens up and the eruption kicks off. But, and this is crucial, not all eruptions are the same. It all comes down to the magma's viscosity, basically how thick it is. Thin magma flows really easily, which gives us those gentle, almost beautiful rivers of lava. But thick magma, that's where things get incredibly dangerous, because that thick, sticky magma traps dissolved water vapor, carbon dioxide, and sulfur dioxide.
As this thick magma rises, the surrounding pressure drops. To picture this, just imagine grabbing a bottle of soda, shaking it as vigorously as you can, and then suddenly twisting off the cap. The pressure instantly drops, and the gas violently rushes outward. Volcanic eruptions work exactly the same way. If thick magma traps all those expanding gases, the pressure just builds and builds until it erupts with an unimaginable, violent explosion, blasting out towering ash clouds and devastating shockwaves.
And this explosive mechanic, it totally dictates the different shapes we see up on the surface. That thin, runny lava spreads way out to create wide, gentle shield volcanoes, like Mauna Loa in Hawaii. But the thick, explosive magma, that builds the tall, steep, iconic peaks you'd instantly recognize. Stratovolcanoes like Mount Fuji or Mount St. Helens. You've also got smaller cinder cones made of piled-up volcanic fragments, and lava domes built from that super thick lava, which are notorious for collapsing dangerously.
But honestly, what's truly mind-blowing is that some of the absolute most dangerous volcanoes on Earth don't even look like mountains at all. They're actually hiding right beneath enormous depressions in the ground called calderas. These are the supervolcanoes, like the ones sitting right beneath Yellowstone. When these erupt, they hold enough power to release thousands of cubic kilometers of material, literally enough to completely alter global climate and agriculture. Luckily for us, these super eruptions are extraordinarily rare.
So, with all that devastating power just locked underground, the obvious question we have to ask is, can we see these explosions coming? Can scientists actually predict when a volcano is going to blow?
The short answer is no. Volcanologists cannot predict the exact, specific moment of an eruption, but they do save countless lives by intensely monitoring the warning signs. Using an arsenal of tools like GPS, drones, satellites, and seismic sensors, they are constantly watching for increasing earthquakes, swelling of the ground, rising gas emissions, and sudden temperature changes. Spotting these red flags early on allows for mass evacuations long before the magma ever breaks the surface. Now, as terrifying as all of this sounds, we actually depend on these violent events. It sounds crazy, but without volcanoes, Earth would be a very different and likely completely dead planet. Volcanic activity literally built the continents we're standing on right now. They created the incredibly fertile soils that support all of our agriculture. They released the gases that formed Earth's very first atmosphere, provided essential minerals, and some scientists even think these volcanic environments might have been the spark for the origin of life itself.
It really is a profound reminder that destruction and creation are basically just two sides of the exact same geological coin. Every single volcano tells a story written deep inside our planet. Each eruption is like a vital heartbeat, reminding us that the Earth is very much alive.
As we wrap up this explainer today, I want you to consider this fascinating perspective. Humanity has literally traveled to space. We've walked on the surface of the moon, and we've sent rovers all the way to Mars. And yet, these massive natural engines churning directly beneath our own feet, deep within Earth's fiery interior, they're still largely a mystery to us.
So what's the big takeaway here? Well, the next time you find yourself gazing at a beautiful, peaceful volcanic peak, I want you to ask yourself, what unimaginable forces are silently building in the dark magma chambers right below you, just waiting to reshape our world all over again? Thanks for hanging out with me on this journey into the Earth's core, and definitely keep questioning the incredible world right beneath your feet.